Green. Good morning. Thank you everyone for joining us today for this Warren lecture. It's my pleasure to introduce our speaker today, Professor Christian Claudel. He's an associate professor in the Department of Civil, Architectural, and Environmental Engineering at the University of Texas at Austin. He has his MS degree in plasma physics from Ecole Normale Superieure de Lyon.
Yes.
And his Ph.D. in electrical engineering from UC Berkeley. So while he's coming to us presented or advertised as a transportation engineering speaker, I think you'll find from the talk today that his interests are a lot broader than transportation engineering and touch many parts of civil, environmental, and geoengineering. So enjoy.
Thank you so much. Thank you very much for the introduction. And for the invitation. So it's my great pleasure to be here today. And what I would like to show is a few works that we have done in the past couple of years related to civil systems and how to essentially develop new types of systems to solve civil engineering problems. So this is joint work with my students, Ahmad, Jezop, Ali, Hassan, who is now a postdoc at UT. And the broad context of this is the advances that we have seen in the past couple of years in terms of computation and sensing. So what is very interesting is that probably sparked by two main things, which are autonomous vehicles and humanoid robots, we have actually much better systems than we had a decade ago, particularly in the field of image processing. So we have now embedded GPU platforms that are super powerful. We can also get very efficient CPUs as well. And that led to a lot of advanced in terms of processing. So on top of that, we have very fast communication systems, for example, to get live video data from other subsystems. So that facilitates the construction of complex systems, essentially. We have also in parallel some advances in terms of sensing and actuation. So for example, we have better IMUs now that are cheaper. We also have high resolution cameras, and now cameras are a main source of information for a lot of systems. We also have much more complex actuators, so that's really something that is coming surely, the revolution of humanoid robots. So people start to build these things now very well, and that comes with a lot of advances in terms of building these actuators, but also with the computational methods for the control, for example, of these actuators. And in parallel, we have also, as I mentioned, advances in computational methods. So in particular, I'd like to highlight a few things. So we can run AI algorithms now relatively easily on these GPU platforms for the training or for the inference. We can also have more complex algorithms in terms of image processing. So for example, we can use fusion of sensors to do simultaneous location and mapping. We can also use complex image processing algorithms like segmentation, etc. in real time. And these things have happened in the past couple of years, really. So we really have, in the context, a much better environment to build complex systems. So I'd like to present two different systems that my group has been working on. So the first one is an augmented reality-based traffic safety system. And the second one is actually a robot that is used to detect microplastics on beaches. So there's no particular connection between these two projects, but just two illustrations of what we can do with more advanced computational tools and processing. So the first thing that I would like to discuss is this ARCAS, so Augmented Reality Collision Avoidance System. The main objective is to try to build a system that would allow pedestrians and other road users to interact and to prevent collisions, but in a collaborative manner. So the motivation comes really from the fact that we have autonomous vehicles that are supposed to avoid cars and pedestrians, of course. The problem is that these autonomous vehicles are not going to become prevalent very quickly. However, what we could do is we could use these augmented reality systems to essentially make people aware of what is around them and increase their performance in understanding their collision risks, etc. And also, we could synthesize directly guidance information in 3D, like in movies similar to Terminator or others. So the goal is to do this, and for this we need some advances. So we need in particular to estimate what people are going to do in the future. So this is a key part. You not only want to track where people are, but you also want to estimate their future actions. So I'd like to show you some past work that we have done that is the motivation for this essentially these predictions. So we have worked with my students Abdallah, so who is now at Meta. And in the past, we have tried to work on an algorithm that was called social SCG CNN, whose objective is to actually predict the position of pedestrians from video data. So you have a video, you have a scene that is monitored from above using cameras. You can track where people are. And in a single pass, what you want to do is you want to predict what people will do in the next couple of seconds. So it's not a very long horizon prediction. It's only a prediction over, let's say, 2 to 5 seconds. But it's still crucial because if you can predict reliably what people are going to do in the next couple of seconds, your traffic safety systems are going to work much better because you can really detect collision courses well in advance to act. So the main motivation was to improve the performance of existing algorithms. So the way the algorithm work in a nutshell, and I'm not going to discuss that too much because that's not the focus of this discussion. The way this algorithm worked is basically taking the position of people from video data. So you have some overhead video system that tracks the position of everyone. And then from the position of everyone, you build a graph, essentially, that monitors, that tracks the interaction between people. So you create a graph that will connect essentially all the users on the road that are within range of a certain distance. And you use actually some empirical function to model the interactions between users. So a little bit like you would use a potential function in physics. By using deep learning, you can actually use that to infer what will be the next positions of the users. So you can predict the future trajectories. The nice thing is that this algorithm sorry, I'm going in the wrong direction. So this algorithm was working pretty well. So in fact, at the time, it was more outperforming all the competitors. The important point about this algorithm is not just the slightly increased performance, but it's also the fact that it drastically reduced the number of parameters. So if you use deep models, you have a bunch of parameters that you have to work with. And this algorithm had much less parameters, so 7,000 parameters roughly, compared to much more for the other models. And that actually boosts the inference time because with this you can predict much more quickly the intents of users. So you can, for example, use that as ensemble prediction to try to predict from a given situation what is the extent of possibilities of actions for each user, if you can predict fast. So that was the first work that we had done. We had done since some other work in trying to predict the more actions of users, but more finely. So not just predicting the locations of users, but also predicting what they would be doing. So this is not really a traffic engineering problem because in this situation, we just wanted to predict the actions of people. So we essentially model the skeleton of people as a graph that is extracted from video data. And once you have this graph, you use similar methods. So you use still a graph convolutional neural network to try to predict the future position of all the limbs of the person and therefore their actions. So it works in a similar way where you have similarly this graph concept to model the interaction between each of the joints in a human body. And you have some adjacency matrix, etc., similar graphs. And eventually you get in one pass the prediction of the skeleta. So you predict essentially if you have a particular position or a particular pose now, what will be your pose in the next couple of seconds and what will be the sequence of these poses. So that's used a lot in predicting the actions of people. But that's not super useful for traffic, of course, because for traffic we want mainly to know where people are going. The next step for us is to work with better systems for data acquisition. So you see that the limitation of this system is that it uses overhead video data or video camera data. With video camera data or overhead data, we don't have the full information that we need. So in particular, we don't know we don't know exactly the attitude of people. We don't know the orientation of their heads. We don't track, for example, their facial expressions, which we don't track their eye movements, and all that are very important predictors on the future actions. Because, for example, if I can track your eye movement and I see that you're looking in a particular direction, that means you're probably going to do something next. So for this, we want to use the AR devices, so AR headsets. This is a picture from RoboCop that has nothing to do with, of course, traffic safety, but that just to illustrate essentially the power of AR, which is essentially giving you complete awareness of what's happening by printing information directly in a very easily understandable way. So if you print just a cross or something, you understand exactly what's going on. You don't have to write text. So you have a much faster interaction with the human, and that's what we're going to try to focus on. So I'm going to show you a quick demo of the system that we have been working on. So in this example video, basically, we have a situation where we have two users at a collision course. So we have one pedestrian in white here, and we have one person riding a scooter. So the scooter rider is hidden behind the wall, and obviously, you want to try to detect them. So here, we are detecting the users and displaying it directly in the field of view. So the person now becomes completely aware of what's happening around them. So of course, we can see on their eye that they are looking at the phone instead of paying attention. Now that's the user again. This is an eye direction pointer. And so of course we can configure when the pointer arrives, and we can configure, the system, like we could highlight with different colors and also. We haven't focused on that, obviously, on this interaction, but the goal is really to try to provide you with maximum information. So the advantage of this type of systems is that you can see through walls. Essentially, you can understand what people are going to do next. And this is only the first step, because, for example, now we don't even have anything about the resolution of this collision. But in the future, we could, for example, draw a safe path. And if we have people that have headsets in both sides, we could tell them, we could make them coordinate, essentially, to avoid collisions, which would be a huge change compared to what we have right now. So right now, when we want to avoid collisions with autonomous vehicles, we see all the users as adversarial, because we don't know what people are going to do, and so we have to treat them as such. So now, how does the system work? So I posted on this video on the Discord about video games to have people react, especially about the shape of the designs and all, and their expression. So of course, some people were wondering how it works, and that answer is wrong. It's not how it works. So I had the same problem with some people from the DOT with whom I was discussing the concept. So the LiDAR doesn't go through the wall, obviously. So the system, the perception through the wall is impossible. So the system works only because we have a monitoring LiDAR or camera that detects the entire scene. And once you have the entire scene and the entire camera that is the entire location that is detected, you can actually monitor the persons. So here, this is the way the system works. So we have two components. We have a fixed component that is, here we are using a 2D LiDAR for perception, but we could use other perception systems like cameras or others. There is a detection algorithm. There is a TCP server that is broadcasting essentially the position of everyone. And we have an app that is developed on Unity that runs on the headset. And that app actually uses some built-in features of the headset, which is, for example, SLAM. So the headset actually uses SLAM by taking the side cameras and the IMU of the headset to calculate its own position in its own frame, world frame. And with this, the outputs are the headset position. So we have the pose very precisely, and that's a nice thing actually. These new VR headsets give you actually positions and orientations extremely accurately, if you want to use that for robotics applications. So with this, we get the head position, head orientation. We have, of course, the headset that connects as a client to the server that gets the information about the position of everyone around, and that computes the corresponding frame transformation parameters to map its own world frame into the world frame associated with the server. And then what we do is we just display the target position in the headset. So we are also working on adding other features to this system, for example, using front cameras to get video feeds. And with the video feed, we can actually process this in real time to get, for example, what people are looking at, and use that as a prediction of the future actions of the users. So we had some debug data that is displayed, and you might have seen that on the video. So here, just to go through the debug data, so it's actually relatively simple. Again, the goal is only to map the two frames. So So what you have is you have to estimate some parameters that allow you to transform one frame into the other. So it's not very complicated. You only have 3 parameters really. And you can track, of course, the current coordinates calculated by the SLAM in the system. And you can get also some parameters associated with the head attitude, so the rotation matrix associated with the frame that was initially conceived by the headset. You can calculate the direction to the target. Of course, that's useful for data, the angles as well, because for the pointers, you need to know where to point. And finally, we have also something that checks the quality of the estimation by calculating both the headset coordinates into the ego frame and calculating the estimated coordinates in the ego frame, but from the LiDAR data. So if the two match more or less, that means that the precision is good. So with this, we can also do some. So here for the automatic calibration, so how does it work? We have really 3 parameters to estimate, the x0, z0, and theta, the angle associated with the rotation that maps these 2 things. So we assume that we have 2 frames that are both flat, and we have a common vertical axis. So that's always the case because the LiDAR frame, I mean, it's relatively easy to make sure that the x and the y-axis of the LiDAR frame are horizontal. For the headset frame, by convention, the y-axis is taken as the vertical axis always when they do the SLAM. So we know that we only have 2 variables, x and z, to work with. So all you have to do is to estimate this matrix, which you can do using least squares. And once you estimate it using least squares, you have to make sure that it's a unitary matrix to make sure that you conserve length. Because of the estimation errors, you might have something that doesn't conserve distances, and therefore that doesn't conserve orthogonality. So all you have to do for that is to take the matrix that you have estimated with least squares and do the SVD and take only the first and the last matrices, so that you ensure that your eigenvalues are going to be plus or minus 1, and therefore you will have a unitary matrix. So here I assume that we have a rotation matrix, but that's only, of course, if the axes are, you can transform one frame into the other just by rotation. It's possible if your convention is wrong that you might have a rotation plus a reflection, if one axis is flipped, for example. So here that's not the case. So some other examples of this system use. So this is an example indoor where someone is looking at their laptop. Someone else is passing by. And again, similar to video games, you have some arrow that points you to look at the person, and essentially you can follow them. Again, as long as people are in range of this system. So here we see the eye vision cues that are on this. So now the person is coming, and so you can see that the pointer is telling you to look at the person. The precision is not perfect, but the errors in positioning are mainly due to the problem of estimating the position of the center position of someone with a 2D LiDAR. The accuracy is not very good for this estimation. With cameras, we could have a much better precision. Okay, so the things that we would like to do next, so I mean, we have been already starting this, so we have now a system that can support multiple targets around, so you have richer interactions, not just one person that is wearing the headset and one other person. You can have multiple other people. We have some limitations that arise quickly because of the LiDAR. We have some occlusion problems, so we have to switch to other systems, for example, with cameras. But what we really want to do next is to move on to other systems. So in particular, we want to be able to support the multi-headset system, where you have multiple headsets that connect into a particular server, so that people can share their coordinates and essentially generate trajectories that are going to be decided for all users collaboratively. So it's a little bit the same system as in the TCAS system on aircraft, where you have when you have a collision avoidance system. So you have some collaborative resolution of the collisions, and we could have a similar system that could arise for cars and pedestrians and bikes and other systems, where basically every player in the collision is collaboratively playing to avoid the collision. Of course, that leads to all sorts of problems in terms of software development. It's going to be pretty difficult to integrate all the possible cases and all the possible reversal cases that happen, for example, in aviation. So in aviation, on the TCAS system, for example, when you have an airplane and another airplane that are in collision course, one is going to go up, the other one is going to go down, but sometimes it doesn't work. The one that is supposed to go up goes down, so you have to do a reverse advisory where you tell the first one to go up instead, etc. So that's a pretty simple case because people have just to go up and down for aircraft, but for us, we have to move in 2D, and that's much more complicated. But that's also, I believe, possible. So we're going to have to use all this. Then the thing that we also want to work on is to port this system into cars. So currently, systems don't work with these systems don't work in cars because they are assuming that you are in an inertial frame when you do the slam. So you need not to have any external acceleration to be able to perform your estimation. But we believe that we could be able to go around that limitation and get something that works in cars as well. So you could have cars and pedestrian interactions. I would like also to mention that right now this is just the beginning. This works on headsets that are working in pass-through mode, so it's a very unsafe system. So you cannot use that system in real life because if your headset, for example, is out of battery, you will black out completely and you will not see anything. So you don't want that to happen. But in a couple of years, we should get new glasses that will be real glasses and that will just display on the glass, which means that if you lose power, for example, you will still see through the glass completely, and that won't be more unsafe than just driving with glasses. Okay, so that concludes the first thing that I wanted to discuss. The second project that I wanted to discuss is a microplastic infrared detection robot. So it's more an environmental engineering problem. The motivation for this, and I'm not an environmental engineer, is to detect microplastics on beaches. So that was some collaboration with the geoscience department at UT Austin. We have lots of microplastics that are entering the oceans, and most of them are degraded by light, radiation, or other things. And they end up polluting beaches whenever you have currents and that go on the beaches. So you have actually some tidal variations, etc., that will bring these plastics on the beach. So mapping these concentrations is very important because if you can map the concentrations precisely, you can detect the gradients, so you can see where you get more contamination. You can also understand the deposition mechanism, so how does it come from wind or does it come from tides and at what rates? And what are the main factors that lead to the deposition of these plastics. And that can lead to better environmental policies. So currently, the microplastic detection is done mainly by having graduate students taking sand and putting the sand in a bag, going back to the lab and doing some technical analysis of the sand to try to detect the plastics. So that's a very thorough method because the method that they are using is actually detecting all types of microplastics from any size. The main problem is that it's not really automated, so you cannot really, each measurement is taking a lot of effort. So we wanted to solve this, and this is a collaborative work with the Matagorda Bay Mitigation Trust that gave us funding for this study. The goal for us is to really automate that process, but I just want to place a caveat. We are going to focus only on large microplastic particles, so particles that are 0.5 millimeters and above. We are not focusing on the very tiny microplastics. So 0.5 millimeter is small, it's not very large, but for microplastics, it's already in the large category. The very tiny ones are very difficult to detect and so we think that we can go down to 0.1 millimeter theoretically, but we won't be able to do much better than this. And we want to have a system that is autonomous, basically, that is going on the beach and tracking the position of plastics to calculate gradients and other parameters for environmental sensing. The inspiration came from, I would say, it came from the robots on Mars that are using. So initially, we started to focus on this problem with one of my colleagues, Carlos Bays at UT Austin, that is an expert in Raman spectroscopy. So this is a field that I have no knowledge of, but that's really the field that you want to use if you want to do analytics of particles. So we wanted to use initially a Raman spectroscope, which is similar to what is installed on the Curiosity rover, but then we dropped the idea, so that was the Raman spectroscope that was installed on the robot, but that's an initial version. That didn't work well because the problem is that Raman signals are extremely weak. They are, for example, if you shine with a laser, you have only 1 out of, I believe, 10,000 photons that are Raman scattered. So it's very, very difficult to get a good signal-to-noise ratio. In the case of the rover on Mars, you can use actually very high power. So they use, I believe, nearly 1 watt of UV, of deep UV radiation. UV radiation also helps a lot because if you have a deep UV, you have a much more Raman return. And for us, we cannot do that, obviously, because we have safety limitations that prevent us from using that much power. Since we are going to operate in the wild over beaches and all, we don't want someone to be blind accidentally because of a reflection. So we cannot use Raman, so instead we move to near-infrared spectroscopes. So near-infrared spectroscopes are going to be easier to work with, the signal is going to be stronger. So the general design philosophy for the robot is to make a robot with 4 wheels, skid steering, battery powered. We cannot actually have too much lifetime with the system, and the main resources that pump power are actually the light source for the infrared spectroscope, because for the infrared spectroscope you need to have a continuous lighting source that actually requires a lot of power. So it's halogen light. And that, of course, drains the battery relatively quickly. So we use a high-definition camera for the detection. So we are using in a high in-hand configuration in terms of robotic. That means that basically the camera is in the arm of the robot. We are going to use it only during the night. That simplifies a lot in terms of thermal control and lighting, etc. And we use actually in this system 2 computers, so Jetson Nano for the image processing and Raspberry Pi for the general control and navigation. So this is the architecture of the system done by my fantastic grad student Hassan, who is now a postdoc. So this is the architecture, the ROS functions that are going to be defined. So it uses ROS and the robotic operating system. So we have several components in terms of hardware. We have the navigation, so we have sensors, GPS, IMU, etc., the classical things, the wheel encoders to know where the robot is going. We have also customized 4 degrees of freedom robotic arm. So we locked actually 1 degree of freedom to have an easier way to operate the system. We have a camera. So the primary way to detect the microplastic is through the camera. So we look at the scene and we try to detect anything that looks weird compared to the sand and natural things. We have also LEDs to light the scene. And finally, for the analysis, so once we have detected a piece of microplastic, the goal is to bring the arm and the spectroscope in position to do a scan and to check the type of microplastic, so to classify it into different categories. So we have different types of plastics like polyethylene, polypropylene, etc. And we just essentially detect the position, take a picture of them, classify them, and move on to the next bit of plastic. In terms of a finite state machine, it's not, again, it's exactly what I discussed. So we have here the navigation part, the scanning part. So in the scanning part, you try to detect if you see a microplastic bit. And once you see a microplastic bit, the next step is to actually be getting some reference spectra. So you have to go close to the microplastic, get a spectrum to get the reference, and then directly onto the microplastic, get the spectrum. And once you have that, you classify it using neural networks to get the type of plastic. So this is the robotic arm that we are using. So that's the core piece of the robot. It's using 4 degrees of freedom, but we have one constraint for orientation, so that facilitates the work. Detection is with this camera that is right here, so it's an autofocusing camera, a very cheap one, like $20, but sufficiently accurate, so it's 16 megapixels. And I don't think we're gonna get much better than that, because if you look at the focus distance, the minimal focus distance, and the amount of pixels, we get about 0.1 millimeter per pixel, but it's probably almost a limit, a physical limit, at least for now. Even if we get much better cameras, we probably are going to improve that number slightly, but not that much. And the classification is done by this part. So this is the infrared light. So the infrared lights come here. It shines onto the plastic. So the plastic size here, it's exaggerated, of course, it's very tiny. And the response is seen by this receiver lens that is connected to a fiber to the spectroscope. So the logic to detect the plastic, so this is where it's becoming a bit difficult in terms of signal processing. So far we did something very simple, which is use essentially highly saturated colors. So that's a bit what we are doing when we try to see if we have plastic on the ground. We try to see if you have something blue or red or something that is really a color that is not natural, something that is saturated. So in that case, you can easily detect, for example, these particles here, the blue and the red plastic. You don't detect actually this yellow plastic in this case. But this light blue plastic here is detected again. So it's something to start with, but we're gonna ultimately move to a machine learning classifier, for example, adapting YOLO type algorithms to get something more accurate in the future. So once we have detected the object, what you need to do next is to bring the arm into position. So to bring the arm into position, we did something relatively simple as well. So we have this arm there. It has its own controller, but we couldn't make it work ultimately because we customized the system too much, so the parameters were wrong. So we did a simple model of geometry of this arm, and we just actually linearized everything. And we calculate the actions at each step using linear state feedback to calculate the next positions of the camera and make that system move onto the target. That's not super efficient, that's a little bit slow. One of the problems for the speed is the fact that this arm can only be controlled, so you cannot control directly the motors, you can only set an initial position, an initial joint positions and a final joint position. So that's how you set it. And because the system is relatively heavy, it has a certain settling time. So each time you move, you have to wait that the system relaxes before taking a new picture and calculating the next steps. But what is important is that the accuracy that you require to get the spectrum is pretty high. So you need to be accurate within 0.5 to 1 millimeter. Otherwise, you cannot get a reliable spectrum of the plastic. So this is an example of how it works. And so that's a test that was next to campus at UT. So this is here the motion of the arm that sets itself in place. So this is how we detect the plastic. So the plastic is very tiny, and this is this pixel right here. That's the microplastic bit. And once it's detected, you see that the system, so this is the source of infrared light, starts to get closer. So first we adjust the XY coordinates using feedback control. Then we are adjusting the Z coordinate, and for this we are using the response, from the infrared light. So we are looking at how much signal we collect. And we get the signal reference, we get the signal of the spectrum and the spectrum, of the plastic, and that's done. So this is the view of the robot. So first we have to get close to the plastic. We have to make sure that we get high enough spectrum signal. And once we get it, so we look, we get the reference spectrum, and then within one step we go directly to the position of the plastic, and we get the final spectrum, which allows us then to classify the type of microplastic. So, so here is an example of what we see with the robot. So this is again with my colleague Carlos Bays at UT Austin, so who published recently the classifier that we are using as part of this robot. So it's a neural network classifier. They did a lot of experiments in the lab. And these experiments allowed us to basically build this neural network model, which from the spectra gives us the type of plastic. So you can see that, so this is an example of a plastic spectrum that is detected by the robot, and it classifies this as a polypropylene, so it's a type of plastic. You can see that the precision that we need to reach is relatively high, so this is the final error plot that we get. So one of the big difficulty that we have is to try to make sure that we go right on top of the plastic. But as we go on top of the plastic, we are losing sight of the plastic because it's actually, the light source is actually making it impossible for you to see what's under a source. So we have to make sure that the final step is relatively accurate. So we get approximately a millimeter errors, and most of the time, in 95% of the case, we don't need an additional step to improve the signal further. You can see the impact of perturbations in the X and in the Z direction. So while when you are nominal, you get good signals. If you are slightly off nominal, you can get signals that are completely wrong. So you have to really be right on the spot in order to maximize your signal. Okay, so now the future work on this system. This is very preliminary. Right now, we have also a very simple navigation logic, which makes you go from one point to from one beginning point to an end point. So we don't have, for example, a system that is adaptive that will try to seek for microplastics at different locations and try to optimize basically its information gain. So it will not try to basically tell you where interesting places are. We are just having a very crude logic of going in a forward direction and scanning, moving around, scanning and classifying plastics. The other thing that we would like to improve are the detection accuracy. So we need to build better models. So we need to, in particular, try to work with YOLO type algorithms to better detect plastics. There are some categories of plastics that are particularly difficult to detect, and that's plastics that have non-saturated colors. So for example, if you have tire particles that just looks like a black sand, if you have a white plastics that looks like a debris of shells, and if you have transparent plastics, depending on the way they are made, they can look like a drop of water or something similar. So it's really a challenging step to recognize this type of plastic. So we're going to work on that. And finally, we would like also to improve the hardware. So we'd like to get a better arm to get more accuracy at the end. And we have to weather-proof that system. So even though we can choose when we are going to test it, you will still have probably some dew or some rain during the night. So we have to make sure that everything is resistant. Okay, so I would like to briefly conclude this presentation. So what I just want to insist on is the fact that we have major advances in all these fields. So in the field of hardware and of systems, we really have now tools that were not available to us previously. So I saw recently a video of someone, for example, just using a VR headset on a robot to get pose estimation. So this is how good the technology has become. So when people were doing robots some time ago, they had to make their own SLAM systems for mapping, for positioning. Now the headset is so good that you can just directly put the headset on the robot, extract the data out, and you will get a centimeter or more accurate positioning in the environments that you are going with. So we have actually much better systems. We have also lots of advances in automation. So we don't see that, but for example, for autonomous vehicles, things are getting better every day. We have advances in humanoid robotics, and we have more and more companies that get funding in this field. We have advances in AR, VR systems. And with this, we can build much, much more complicated systems. So I feel like almost that we are on another layer of abstraction compared to what we had before. So in the history of mankind, we started, for example, with very crude systems that were just, batteries and simple capacitors and resistors and, trying to make something work. Similarly with mechanical systems, with mass dampers and all. We went from that to computers, which are a complete change of paradigm in the development of these systems. And now I feel that we have another level of intelligence and capability that we can actually exploit to build better systems. That's my conclusion. Yeah. Thanks.
Thank you. Do we have any questions from the audience?
Thank you for this amazing talk. I have a question about the prediction system, the pedestrian prediction system, and the AR component. So, what happens if the prediction system kind of fails to predict the future movement of like unseen pedestrian?
That's complicated. Yeah, absolutely. So right now, I think this approach will be done incrementally. So initially, it will all depend on the penetration rate of this system in the population. My hope is that these AR glasses, if they become available, will become prevalent. So again, that's a hope because it never materialized. This is very funny about AR and VR systems. If you look at old movies like Back to the Future, you know, they still had the newspapers in 2025, but they would have AR glasses, and so I don't know why in the past always people assumed that we would have AR, VR. It didn't work that much, but I believe that it's mainly because we don't have the killer app, the apps for that are very useful. So I think if we have this type of apps that have very high utility to avoid accidents, you can have mechanisms, for example, to increase adoption by having people pay discounted rates on insurance, on car insurance or other mechanisms. And again, we'll have to build that system, assuming that, again, you don't have everyone that is perceived. So if you have someone that is not perceived or that is not equipped with that system, you have to treat it in an adversarial way because it's not going to be part of the cooperative game. And that's something very complicated. I'm not sure exactly how to get started on this problem, but all you know is that if you treat everyone in a collaborative way, you could have potentially a very high efficiency boost. I'm not sure how much that will degrade when you have a few people that are not part of the system, but I would still hope that a lot of benefits remain in that approach. But really, the key thing is to try to treat people in a collaborative way. That's, for example, when you're driving a car with an ADAS system that is avoiding colliding with a pedestrian when it's in front of the car, you still treat the pedestrian as an adversary in the system. So you still have the car that must brake, but you never have any coordination. If you had, for example, the car trajectory as a pedestrian, if you see the car and you see, for example, an arrow that is painted right in front of you, that's the path of the car, you're not going to cross the road, and you know you have a collaborative decision making that will improve efficiency.
Other questions from the audience? Otherwise, I have a question. I was wondering again about the collision avoidance system. It seems to me, and I might have misunderstood, it seems to me that it's a centralized system. So there's one centralized node that does all the tracking, and then shares information with everyone. But if you were to deploy this at a large scale, you'd probably need some sort of distributed system.
That's right,
Could you, how would you do that?
So it's possible to do this. We have been thinking about this exact problem. With the headsets, they have their own simultaneous SLAM algorithms that they can run. So the main problem is that, of course, nobody agrees on where is on a common reference frame. But now, if you start to put this with a fusion of cameras data from the own headsets, you can also track the headsets around you, and you can make some algorithms that will basically make them agree on a common frame of reference. And with that system, you could have a distributed system that would be purely able to adapt. Again, that all depends on the range of communication, of local communications and others, but it's possible to build this type of system. What I would like also to investigate is the interaction with the ADAS system, like advanced, like adaptive cruise control or this type of mechanisms. If you have some feedback for the driver, that's going to make the driving of the car much more safe and much more easy. Particularly, for example, for things like lane assist and all. One of the big issues of this ADAS system is the fact that the drivers don't understand what the car is doing, and they don't even understand if the car is right or wrong, and that brings a lot of issues. If the car directly tells you, I believe that you have an obstacle here, that's why I'm swerving, if you don't see an obstacle, you're going to prevent the car from doing something wrong, and that will facilitate essentially the interactions, just the ability to visualize.
Any additional questions from the audience? Otherwise, I have more questions. I can keep going. Okay, I'm wondering on the plastics robot sensing part. What's the just ballpark? What's the 6 hours? Is what you said the battery life is. How much beach can you scan in 6 hours?
That's very slow. That's a slow process. So it's going to be probably we estimate, going to do about 10 meters an hour. So probably 60 meters of beach. That's what works.
And how wide of a
approximately half a meter or something. That's going to be there. But we are trying, I mean, again, we are trying to get started on the automation phase. So it's not super fast, but what is very interesting is the ability to automate it for the people that will work on it. Because even if it's not super fast, if they can scan, for example, day after day, the evolution of things, that's a huge help.
Yeah, go ahead.
So is there any things that, like, in the future with increasing processing power we can't do now, but we'll be able to do?
Yeah, I think there are lots of things that we will have to do, and I mean, for society in particular, these man-machine interactions, because we keep talking about autonomous vehicles, autonomous robots and all, but the elephant of the room is that you're not going to work with these systems if you don't have a confidence on their actions. And for example, if you have a robot that is next to you, how do you know if the robot is going to do something unsafe? How do you react with these machines? I think this ability to visualize, to understand, to have advanced processing. And again, I'm making the case for AR, so because it has display capabilities, but that's not the only thing for AR. Of course, it has display capabilities, but the real important thing is that it has a whole lot of sensors in comparison with smartphones. So I experienced the revolution of smartphones back in the 2000s, and for us it was super valuable, for example, to collect traffic data and all, because you had at least a system that would contain, for example, a positioning system, light data, IMU, etc. So that's super useful, but that's nothing in comparison, for example, with something that's on your head that scans what your eyes are looking at, that can even interpret what you are looking at, because you can take the video data and do segmentation, and you're looking at that object, etc. That can also detect your facial expression, so your state of mood, and that has an importance for the human-machine interaction, because if you're angry, for example, driving a car, you're not gonna get the same actions, in a traffic safety system as if you're quiet, or if you're so all this type of sensing that is only available because you're scanning the head, and you get the eye motion, the facial expressions, the head orientation and all, and the limb motion too, because these systems can track hands and all. I think that's gonna be like the smartphones. That's gonna open a whole new type of apps. Smartphones actually were the key thing for a lot of apps, because smartphones allowed you to have Uber, for example. You had positioning, you had an ability to have a credit card to pay to, etc. So that enabled these apps. But that's still nothing in comparison with what you can do with more advanced sensing. And I think wearables and all these things, that's going to be super important, particularly if we have more and more humanoid robots or AVs, or or partial automation that is becoming increasingly prevalent. We'll need to have a better interaction with that world.
If there's no other questions, let's thank Chris again, and thanks everyone for attending.